This lesson is about solving inequalities by graphing. Here's an inequality in two variables. Notice the x and y. And let's start by posing the question, for what values of x and y would this be a true statement? What if x were 10 and y were 2? These are just numbers I chose randomly to get you to think about something. If we substituted 10 and 2 into the original inequality, notice x was replaced by 10, y is replaced by 2, and we did the algebra, we would discover a true statement. 14 greater than or equal to 12 is a true statement. And that means that x equals 10, y equals 2 is a solution to this inequality. Now, I'm not suggesting that you randomly plug in numbers to solve inequalities, but it's worth noting that this inequality can be true for certain values of x and y. What if I changed y to 5? Again, I'm not suggesting that you should plug random numbers into the problem. That's not an efficient solving technique. But for the moment, just think about these two values. If I were to plug them into the inequality and did the math, I would get a false statement. 3 is not greater than or equal to 12. So what this shows is that there are certain pairs of values that make inequalities like this true, and there are other pairs of values that make the inequality false. And what this seems to indicate is that we might be best served by looking at where on a graph we can find ordered pairs of x, y that make it true, and where we can find ordered pairs of x and y that make the inequality false. So let's pick some random points here. And we'll chart the true and false results on the graph. If I were to randomly pick x equals -2 and y equals -6, again, this is a total arbitrary choice, and I'm not suggesting that this is how we solve a problem. We're not at the how to solve these problems yet. We're just at the stage where we want to investigate what things would make this inequality true and what would make it false. So here's some random values. When I plug them in and do the algebra, I get a true statement. And that means that the point -2, -6 makes the inequality true. So I'm going to put a T on the graph at that point, at -2, -6. Well, I found one solution to the inequality. I'm sure there are more. Let's pick another random point, 1, 1. If I substitute 1 for x and 1 for y, and I do the algebra, I get a false statement. So I'm going to put a false at the point 1, 1. How about the point 5, -1? Just a random chosen pair of numbers. When I substitute them into the inequality and do the math, I get a true statement. 13 greater than or equal to 12 is true. So 5, -1 is a solution to this inequality. I'll put a true at 5, -1 to indicate that. Here's another random pair of numbers, 5, 0. Plugging in 5 for x and 0 for y and doing the math gives me a false statement. 10 greater than or equal to 12 is not true. Therefore, 5, 0 does not make the inequality true, and I'll put a false at the point 5, 0 to indicate that. Now, this is not a good strategy for actually solving this inequality by graphing. But what this shows is that there are some true points and some false points for any linear inequality like this. Now, what if we were to continue this procedure and continue to try points over and over and over again? Well, first of all, imagine how tedious this would be, which is why I'm not recommending it. But it's still important to understand that if we were to continue to try this process over and over, some points would be true and some points would be false. But what's interesting is that all the true points tend to congregate together, as do all the false points. Now, you wouldn't actually go through the arithmetic of trying this many points. It's horribly inefficient. But what it does show is that there seems to be a dividing line between all the truths and all the falses. And if we could find that dividing line, then we wouldn't have to go through this lengthy trial and error process. So now let's turn our attention to what the final answer to this thing would look like, and then more importantly, how do we find this dividing line? Well, first of all, when solving an inequality of any type, we don't care what values make it false. So let's erase those. But rather than writing true, a bunch of T's underneath the line, mathematicians tend to just shade there, and that shading represents that any point in that section would make the inequality true. So we'll use shading instead of writing a bunch of T's over and over. But the real question is, how would we find that dividing line in the first place? Well, in order to find that dividing line, you need to graph the corresponding equality or equation. Notice this. In other words, if you change the problem to an equals and you graph it, you've got your dividing line between your trues and falses. So the question is, are your graphing skills, your line graphing skills, good enough to follow the rest of this video? Because this video assumes that you have some decent command over graphing straight lines. Now, there are other videos you can watch to learn how to do this. Some of you may remember the intercept method. Some of you may remember the slope-intercept method. Now, this video you're watching now is not designed to reteach those. There are other videos for that. If you feel like you need to go back and review graphing lines, now would be the time to do that. But for those of you who feel comfortable proceeding, let's go on. If we were to graph this line using whatever techniques of the past that we know, we would have the dividing line between the trues and falses. And then instead of doing trial and error with tons and tons of points, as you saw earlier, I could just pick one random point, substitute that into the inequality, and find out whether it's true or false. Turns out this point is a false point. Or if I picked a point on the other side of the line and plugged that into the inequality, I would get a true statement. So it seems as if I picked one point on each side of the line and plugged it into the original inequality, I would know which side was my true and which side was my false, and then I could shade accordingly. But even more efficient is to just pick one point on either side of the line. My favorite point, personal favorite, no rule says you have to do this, but my personal favorite is the origin. I love the origin as a test point, 0, 0, because plugging in 0, 0 makes for some really easy arithmetic. 0 greater than or equal to 12, that's clearly a false statement. And that means the origin, my test point, must be on the false side. And that leads me to conclude that the true side must be the other side. And then I would shade there, and I now have the final solution to this problem. Well, what this shows is that any point in the shaded region makes it true or is part of the solution, and any point above the line in the non-shaded region doesn't make the inequality true, and therefore is not part of the solution. But one thing we haven't considered yet is, what about the points on the line itself? Points not above or below the line. Let's investigate that. Here's a point on the line, randomly chosen point on the line, 3, -2. If we were to plug 3, -2 into the inequality and do all the arithmetic, something interesting would happen. We would get 12 on both sides. But 12 greater than or equal to 12 is a true statement. So that particular point on the line is true. Let's pick another point on the line and see what happens. Random point on the line, 0, -4. If we plugged 0, -4 into the inequality and did the arithmetic, the same thing would happen. We would get 12 greater than or equal to 12, also a true statement. It turns out, if we were to keep doing this, every point on the line would be true. So what this problem shows is that every point on the line is true, every point underneath the line is true, hence the shading, and every point above the line is false, and therefore there's no shading there. And that's the final answer to this problem. Let's change our attention now to this symbol here, this compound inequality. What if we were to change that compound inequality to a strict inequality, a pure greater than in this case? Let's once again examine what would happen to the points on the line. Random point on the line. When I plug that point into the inequality and do the algebra, I still get 12 on both sides, but I now have a false statement. 12 greater than 12 is false. A number can't be greater than itself. So in this particular instance, that is a false point. Let's examine another point on the line. Once again, 0, -4. Plugging in 0, -4 and doing the algebra produces the same false result. It turns out, with this strict inequality that we've now changed the problem to, all the points on the line will make the inequality false. So that discovery left mathematicians with an interesting question. If all the points underneath a line make the inequality true, but all the points on the line don't make the inequality true, and therefore aren't part of the solution, how do we draw that? What do we put in our drawing to indicate that the shading is a true region, but the line itself, the border of the shading, is a false region? I suppose we could not draw the line at all, but that might be a little confusing. So for clarity, mathematicians have decided to put a dotted line. And what that dotted line represents is that none of the points on that line are a solution to the inequality. They're all false. But the shading underneath it represents the fact that any point in that shaded region, as we saw earlier, would make the inequality true. And that is the final answer to this problem. Let's do one more example. So we're given an inequality and asked to solve it by graphing. The first thing I'd like to do is find that dividing line between all the trues and all the falses. So I'm going to graph the corresponding equation. Notice I've changed the inequality to an equal sign for the moment. Now again, not everyone is comfortable with graphing lines, and you may have to go back and see other videos. But if you are comfortable graphing that line, you will eventually discover that it's right here, using whatever methods that you have at your disposal. And so now that I know where the dividing line between all the trues and all the falses is, I just have to figure out which side of this line has all the trues and which side of this line has all the falses, so that I can shade the true side. To do this, you could pick virtually any point. You could pick any point that's not on the line and use it as a test point. My favorite point is the origin, only because it makes the arithmetic so simple. So I'm going to use the origin as my test point. Plugging in 0, 0 and doing the arithmetic leads me to a clearly true statement. 0 less than or equal to 3 is definitely true. And that means the origin is in the true region. Should I pick a point on the other side of the line and test it? Well, I could, but I would just find out that it was false. Either one of those would lead me to the conclusion that not only is the origin true, but any point underneath the line is going to be true for the original inequality. So all I have to do now is shade underneath the line, and I'm done. That's the answer to this problem. Final thought, what if I were to have picked a point above the line? Any point above the line would be false, and therefore there's no shading there. And one more thought. What if I were to change the compound inequality to a strict inequality? All the points in the shading would still be true, but all the points on the line itself, on the boundary of that shading, would be false. So I would indicate that by replacing my solid line with a dotted line. And that concludes the lesson.